from the world leading institutions like University of London, Salford University, Bordeaux University, including our IIT Kharagpur, Anna University, SRM University, and Rajalakshmi Engineering College. In addition to that, we have the two important persons to handle the sessions from the UCOL Aerospace and Advanced CT Composites Materials Company. Hope this faculty development program will be fruitful in the field of materials. I welcome you all once again. Thank you so much. Over to Professor Tamilvendan.
May I invite and request our beloved principal, Dr. J. Jaya, to deliver the inaugural address for the faculty development program. Over to Principal, ma'am.
Thank you, Professor. Warm greetings to one and all present over here. It gives me immense pleasure in joining the inaugural ceremony of 5-day faculty development program in association with Aeronautical Society of India on the title Advancements in Aerospace Materials, Manufacturing, Testing, and also Characterization. So it is a very privileged and a proud moment for every one of us. So I am congratulating and acknowledging the hard efforts taken by the Aeronautical Department members of faculty, in particular, Head of the Department, Dr. Gopinathan, Professor Tamilvendan, and Professor Veeramanikandan, and the entire team for their painstaking efforts in organizing such a wonderful event for the beneficial of the teaching fraternity. Our appreciation goes to all of them. So with respect to the subject, composite materials, in Hindustan College of Engineering and Technology, most of our professors are doing a great, wonderful research work in this area. Especially the professors from mechanical engineering, mechatronics engineering, and some sizable number of professors from physics department are also undergoing their research in composite materials. So, keeping the importance of the field composite materials, this particular title has been rightly taken for the discussion as well for the deliberations for the entire 5 days. So, I am requesting all the teaching fraternity who have all gathered here, who have all spent your time for this entire 5-day span, kindly pay good attention, because you know, like there are eminent professors from like our Dr.Devendran Thirunavukarasu, founder and technical director, ST Advanced Composites Chennai. Welcome you, sir. So, like the professors from various parts of our nation, and also eminent professors from abroad also have kindly consented to be the speakers of these entire FDP. So, I'm requesting all the members have assembled here to pay good attention for these topics. So once again, I welcome all the persons gathered here. Thank you and all present here.
Thank you very much, ma'am. Thank you for your kind words and the address. May I now invite and request our respected CEO, sir, Dr. K. Karunagaran, to deliver the felicitation address for this ceremony.
Vanakkam and pleasant morning, all of you. Most respected principal, the very much experienced resource person for the day, Professor Gopinathan, and the team from the aeronautical engineering, and dear learned colleagues, the participants. On behalf of the management of Hindustan Educational Institutions, Coimbatore, I, the CEO of this organization, warmly welcome all of you to join for this 5-day faculty development program organized in association with the Aeronautical Society of India. I must appreciate the effort of Dr. Gobinathan and his team for bringing this 5-day FDP. See, arranging 10 speakers at least for a 5-day program, such a difficulty is there getting eminent speakers for a 5-day program. Anyhow, this 5-day program is going to be useful for every one of you, I tell you, because when your participation certificate goes back to your campus, that is going to carry mark for the NAC or NARF ranking programs, because they are looking for not less than 5-day participation, either in the form of STTP or FTP, in a way that is going to be helpful for your institution also. Coming to the topic, advancements in aerospace material. We all know that how AI is evolving in a big way in the world. In the similar way, the materials also, whose specialized characteristics also being put into use in most of the industries now. Smart materials are being used worldwide in many applications. Aerospace industry is one of the industry which is making highly useful of these materials. So in a way, I think this 5-day program will connect a lot of inputs to all of you. Probably some of you may design some of the area which is going to be deliberated even maybe for your research area. In a way, I think the speakers are going to lined up for this FDP is phenomenal. I must once again congratulate Dr. Gobinathan and his team for arranging such a wonderful FDP with the eminent speakers. Coming to the learning process. Yes, of course, even through this FDP program, we all are going to learn. I'm also willing to sit for some of the areas because I have touched these areas during my research program somewhere in 92, 93. So I'm also very much interested to sit for some of the sessions. See, as per the words of Albert Einstein, never stop learning because life never stops teaching. Of course, every moment in a teacher life is supposed to be a learning. Even the Washington Accords 12th attribute clearly and importantly says for our teaching fraternity is that lifelong learning. It is not only for students, it is more applicable for the teaching faculty. So in a way, you will accept it. I would like to just end up with a quote from our people's president, Dr. Kalam. All of us do not have equal talent, but all of us have an equal opportunity to develop our talents. Let this program also be an input to develop your talent. Thank you so much for this great opportunity. Wishing all of you to have a great learning out of this faculty development program. Over to the organizer.
Thank you, sir. Thank you so much for your inspiring words. May I now take up this opportunity to welcome and give a brief address about our today's resource person of the first session of the 5-day FTP, Dr. Devendran Thirunavukarasu, founder and technical director, ST Advanced Composites, Chennai. We welcome you, sir.
Thank you.
Mr. Devendran Thirunavukarasu is the founder and technical director of ST Advanced Composites, Chennai. He has a hands-on experience in composite manufacturing while studying in France and as a composites engineer training in Italy. His skills include computer-aided design, manufacturing technology, product development, composite testing, and certifications. STAC, that is ST Advanced Composites, is based in Chennai, India, and started in 2014. This startup initially had an inspiration while he was doing his trainee program in 2012 at Italy, even with a job opportunity in Italy, which he refused to take up and return to his country to work on his dream. Focusing on development and implementation of sustainable composite materials to solve the climatic change and the environmental issues. He has experiences in bio-nano composite materials, and fiber reinforced composites. We are very happy to have such an eminent and experienced researcher and entrepreneur to be our resource person for this 5-day faculty development program. Thank you very much, sir, for being here with us. And I thank everyone, and over to the resource person. Thank you, sir.
Hello.
Yes, sir.
I'm audible?
Yes, sir, you're audible.
Yeah, okay. Very good morning to all, and thank you for your warm introduction. And I'm thankful for the admin of Hindustan College of Engineering and Technology and the CEO of the organization, Mr. Dr. Thirunavukarasu, and also the HOD of Aeronautical Department and the principal of Hindustan College of Engineering. And also the thanks for your introduction. So the first, I thank all of the participant in this the faculty development program. So yeah, Mr. The Tamil Vendan is already give my the introduction. So I'll give a short introduction of our company and what we are doing and how this is started, and I'll give that some brainstorms here, and then I will explain and I'll present the research works. I am going to present two of our in-house introduction. Sorry, the in-house research work. So first, I'll present our company's profile and I'll explain what we are doing. Yeah, my screen is visible, right? Hello? Hello? Yeah, my screen is visible. Okay. Yeah. So the ST Advanced Composites, the ST is mostly we are working in a high performance composite material like carbon and Kevlar, and we are developing some natural fiber into the advanced composites. So the why that advancement in the natural fiber composite, I'll tell it in my research work. So the ST Advanced Composite is based in Chennai, in Madurai, and we started in 2014. Currently, in that time, we are working on the aerospace and also the motor sports parts. So then right now we are into all the sectors. Like in marine also we are working, and some of our clients, they are giving the problem statement, and we are finding the solution, and also we are giving this the solution for lightweighting and improve their the performance that product. Even in the marine, and right now we are working with L&T shipbuilding. So they are facing some problem their shipyard, and we are giving some solution using the composite materials to resist the corrosions, and also so to improve that the impact resistant and then the tide waves. And that is one notable the client currently we are working with for solution problem and solution statement thing. And other thing in the aerospace, we are working with the DRDO for the projects, and we are and also we are working with overseas. We have an aerospace projects also there with Dubai Space Center. We are supplying carbon fiber parts for Dubai Space Center, also the UAE Space Agency. And this is a notable client right now. Maybe in the other slides I will explain in detail. So it started from the motorsports, and in the aerospace. Initially we are working on drones and unmanned air vehicle structures. Currently we are producing the real-time aerospace projects also and products also. In the later on slides I will explain. So we are giving quality because we are not compromising in the quality in our organization. If because without voids and without any delaminations with our facilities available in our company and in India. So we are trying maximum. We are trying giving the highly the quality and also the good product to our customers. Right now we are delivering. So this is the methodology we are following in our company. So initially we are getting customer requirement, because we are not only focusing on a single sector. So it's a multi-sector solution providing company. So that's why we are getting a solution of the problem statement from our customers. So our team is working on it, and we will find the solution. Like from the design also we are supporting, from the design and optimization of the design and the material selection and process selection. And the tooling is there is if they need a single product like a prototypes or a single time product or a multiple product, based on that we can select the tool. So because the tooling is the cost factor is a high tooling, we have to spend more money on tool manufacturing in the composite industry. So so we are working on the tooling material selection in a soft tool or the permanent tool. The soft tool means it's a temporary tool for a single prototype. So based on our customer requirement, we can select the tooling material. Then the prototype, from the prototype, we are also providing the testing solution, the testing. Maybe if they need any componental testing or a coupon testing or full-scale testing. So we are supporting, and we are collaborated with the universities, and also we have tie up with the IITs on the private the laboratories also. We are collaborating for the based on that the project we are tested in various the institutions. The product manufacturing currently we are supplying a low volume up to 500. We are managing in our facility from the proto to the 500 we are supplying. For in the aerospace, mostly minimum volume is 100, because they are getting in a batch wise production. So that's why we are supplying like that. And assembly in our the composite manufacturing, after that they need some the additional the metallic structure bonding and assembly they need. So that also we are providing the secondary bonding of the structures and inspection using visual inspection from the starting. The basic is the visual inspection. Then we are doing NDT for ultrasonic test. Also we are for aerospace and other structures we are providing. Then the packing and delivery. This is the process we are following in our company. And also we are supplying material for institutions for R&D purpose, because we are supporting students for projects. So we are giving internships and also the training programs. We are conducting training programs for faculties and students. So the time they give, we are introducing the advanced materials to them, and they have we are giving the hands-on training also. The before COVID in 2018 and 19, the VIT Chennai and also the many and also some universities we are directly conduct the development programs also we are conducting. So that time we are supplying materials for their R&D. So this is other materials we are supplying, like vacuum bagging system, resins and core materials, and the nano materials also we are, because currently we are trying to implement the nano materials into the real-time products using carbon nanotubes and graphene. And these are the 2D and 3D the materials also we are implementing into structural and also the functional products. The functional products like the batteries also currently we are working with one company, so we are giving a solution for them. This is a design and analysis part. So from the design and analysis, we are because in India composite design is very expensive, and also the companies, they are not using the exact composite design analysis. So here we are providing the exact what. So even in a Boeing and Airbus, they are also using same thing that we are following here. From the layer wise analysis we are planning, because the composite is two different material. It can combine as a single material, and we get in a good property in that. It is engineered material. So there is some the factors are there, the play orientations and also the material properties. If we change the orientation, we can get better properties. Here we mentioned the 0, minus 45 and plus 45, 90. If you use a 0 and 90, we can get a better tensile and compression property. The plus or minus 45 is hello.
Yes, sir, you're audible.
Right? Yeah. Okay. Yeah. So the plus or minus 45 is flexural and the impact strength is better. So we are giving the complete solution from the in the design projects. So we'll take a problem statement from our customer if they are facing any the impact issues or any the structural instabilities is there. So we are initially we are doing that calculations. Then we can make that the fiber orientations, and we are going to the analysis and answers, and also we are using abacus also. So we are providing design optimization and also the fiber the finite element analysis. And apart from that, we are giving the CFD analysis and thermal also we are supporting. And the advanced metallic and composite tools also, we are some of the companies we are supplying tools for glass fiber, the FRP tools also we are supporting. And the metal tools, we are exporting the tools to the other countries in Oman and Dubai. So we are supplying that tool also. There is different types of tools. I mentioned it in the 3D printed mold also. We are using tool, picture and tools and carbon fiber tools we are making. This is a reusable bag and this is a blader mold, and this is a closed type of molds, and this is a machining and processing of. Also, we are doing consultancy for the tool development. So this is a prototyping service. The prototyping is from the basic. From the basic is a clay modeling. For in all automotive companies, initially they start with the industrial clay modeling, then the 3D printing and the foam cutting. The foam is and the smaller prototype we are using the foam, and the wooden prototypes is also there. That is the medium density fiber board that is available in the market. So we are using that kind of wood in the machining process. And the carbon fiber prototyping also we are doing based on our customer requirement. And the testing we have in-house, we have only 1 or 2 testing facilities, but other thing we are collaborated with institutions and also the laboratories, the private laboratories in Chennai and all over Chennai. And some of the samples is tested in the PSG Coimbatore. So we have a tie-up with PSG. So with their we have the material and they tested for our samples. So this is a manufacturing techniques currently we are following in our company. So the electric curing oven and the compression molding we have, and vacuum bagging technique, and closed mold and resin infusion for our larger structures, and blader mold for the blade and other kind of structures we are using, and the roll wrapping. Based on the project and the customer requirement, we will select the process, because the budget is for customers and their requirement. So we are satisfied all the things are based on their requirement. So and also we are giving that the technical support and the training programs for engineers, and also the research scholars and students in institutions also. So these some of the products we have been supplying for this carbon fiber tubes and sandwich panels and plates is for the drone manufacturers, and the university students also, they are buying this kind of products for their college project, and also the competitions for drone and other structures. And these custom products also we are giving. This race car we initially start with the motorsports. So we have this kind of product lines we have, and this is a carbon fiber seat, and also this is a monocoque structure for race cars, and the battery box, and this is a 1 meter size blade for the unmanned air vehicle. This is a suspension linkages. So in the previous slide, I mentioned the training programs. So in the training programs, we provide this laminated kit for the participants. Then we are giving the training program, the hands-on training program we are giving. So this are the success stories, but we mentioned it up to 2016. After that, I'll show some other thing in the other slides. So here in the 2015, we got a stall in Defense and Aerosupply India. So that we presented our products, and we in the bulletproof helmet, one of our product we are doing R&D in our company. So we presented there, and we can get a good tie-up and also the introduction with the companies. And this is 2016. We got a stall in JEC Composite Asia. This is the largest the composite trade shows in India. Sorry, in world. So we got a stall, and we also presented here. There we got a lot of collaborations, and the introductions into the international market. So these are the teams currently we are supported. This is IIT Bombay, and this is SRM University and IIT Madras, and this is VIT Vellore, and this is Chitkara University, Punjab, and also this one is IIT Madras. So we are sponsoring the teams, and we are guiding the student how to manufacture that monocoque structures of, and also the composite panels for their vehicle. Yeah, these are the current the R&D projects. We developed some product in our company. Still, we are doing research, and we are developed some the indigenous product. This is first thing is high performance thermoplastic composite ballast helmet. Still, this project is on in progressing, because we haven't we did only the static test. We have a dynamic test is we are planning. Still, it's having some. We are waiting for the collaborators for this project, and this is a monocoque structure for electric cars. It's a two-seater electric car. It's a single monocoque structure with aluminum honeycomb. So this third one is the development of UAV CFRP blades for unmanned air vehicles. It's a 1 meter length, and this is a fire retardant panels. This is a laptop stand for. This is one innovative product we developed, and this is a FRP tool we have manufactured for custom design, and this is the natural fiber reinforced the helmets for some commercial applications. And this project is typed Titan for the watch strips, but this is expensive, so we just develop as a proto. Yeah, that's all. This is our company's short introduction. Then I'll move on to our today's presentation. Hello? Hello? Hello?
Yes, sir. Audible, sir.
Audible. Okay. Yeah. So now I move on to this today's presentation. Today I'm going to present the development and the characterization of natural fiber reinforcement, the reinforced thermoplastic composites. Because today the faculty development program is the characterization of aerospace materials. But here today I'm going to present a natural fiber. Why this the interlink between the aerospace and natural fiber means we are trying to use a natural fiber reinforcement thermoplastic into the interior of the interior materials for aircrafts. So that is our idea. But we have many qualifications. We need a qualification for materials, currently developing material, because if we are going to use the natural fiber reinforced thermoplastic material into the aerospace or aircraft interior, we need a lot of qualifications. But here we are using thermoplastic. I mean, the thermoplastic is already currently you're using in interiors of aircraft. Currently, they are using high performance plastics like the PEEK and PPS and also PEI that are high performance plastics is withstand up to 350 degrees Celsius that they are using. But now we are trying to implement the natural fiber, because our company is planning to develop a sustainable composite material. So currently there is a lot of the waste. If you are the aircraft is into the end of their life, so there is a lot of waste is producing, and also the recycling and many things are there. So if we are use the natural fiber composites, one is we can easily recycle and also the decompose. And the thing is, the recycling of the material is also that we need a high energy consumption and also the manpower and cost. The many factors is involved in the recycling of the plastics. So here we are using a natural fiber, the reinforced thermoplastics. We can reduce some of the cost reduction is possible. So that's why we are trying to develop the natural fiber reinforced composites for interior applications. So,
sir, excuse me, sir.
Yeah.
Sir, can you go to the presentation mode, sir? It is
not visible.
Visible, sir, but all the slides are visible. I think if you press F5, it will be there.
Yeah. It's okay.
Fine, sir. Fine, sir.
Okay. So here we took the flax fiber. There is many fibers are available in the market right now, and also we are still we are searching from the nature. Even in Tamil Nadu, there is a lot of the fiber waste are there from the agro waste, and also the banana is the good material, and also there is a lot of waste producing in a southern part of the India. And if you go in the northeast, there is a jute and bamboos are there. So we have a lot of resource in our country. So I took this the flax fiber because flax is already proven in other countries, in Canada and also the US and the Europe. There, it's currently available in the market. The prepex is also available. So that's why we took the flax fiber as a reference. Then we start with the research. So the advantage of the flax fiber is very low density and low cost, recyclable and potential reinforced material. So, and the flax, the flax seeds, it's available in market. They are producing, they're copying in the countries like US and Canada. They're producing that the large flax seed growing there. So the flax fiber as a reinforcement, we have three different the fiber categories. This fiber one is then the fiber content is up to 98 to 99%, and the fiber flax 2 category is 85%, because there is some impurities are there. Here the fiber one is it all depends on the quality. So here the fine and the fiberization is there up to we can yield 99% of fiber content. Here there is a lot of the impurities are there. So that why you are the 85%, because here the processing cost is there. If you need a pure 99% fiber, we need a higher processes. So that's why the cost is included in here. And the fiber flax 3 category is a 42%, and there are a lot of impurities and some waste materials are there. So this fiber 1 is we can use it as a reinforcement for composite, and fiber 2 and 3 we can use it for insulation panels for houses and alternative construction materials. We can use this kind of thing. Okay, so this is a composition of the biofiber. So the biofibers is a structure is they have these 4 kind of the ingredients are there: cellulose and semicellulose and pectin and lignin and wax, and also the water content is there. So high category is the flax, hemp, jute and sisal. The jute and the hemp is we have it now. The India is also, we have the source, and flax is also some percentage we have. And here the categories I mentioned, the cellulose, because in the cellulose is an important material to reinforcement, and also we need this the cellulose alone for our the composite. So here we have to initially we have to do the red train process and alkylation treatment of fiber. So we have to, first step is we have to remove the water content from the fiber. Then the second is we have to remove the wax. Just the dissolved in the hot water itself, the wax is removed. And the pectin and lignin, this too is the hardened material from in the bio natural fibers. And the pectin and lignin, we have to use alkylation treatment or acid hydrolysis, so we can remove that part. But right now the lignin is they are using for reinforcement. The lignin is kind of natural fiber thermoplastic. So currently some of the companies, they are trying to use the lignin as a raw material for the many applications in Europe. And the hemicellulose also is used, but it's when we do that alkaline treatment and acid hydrolysis process, this 2 part is removed. And finally we can get 44% of cellulose. We have a good we get a good reinforcement strength in our composites. The biocomposite is consists of the polymer as a matrix, biopolymer as a matrix, and the fiber as a reinforcement. So these 2 material we can get a composite and engineered material for many applications. The interest of using the natural fiber is the reinforcement is currently having good currently the many applications. So that's why they are using natural fiber. Some of the potential application in this kind of panels is the doors and the instrument panels. And our scope is we are planning to use this kind of parts into the aircraft interiors. But the aircraft interior parts, we need a qualification test, and many we need a certification from the agencies. So I think it take so much time and so much years to get approval for this kind of natural material as a. But there is another applications also there in especially in aircraft manufacturing. Yeah. So this is a biocomposite production. The fiber production, and so the first step is we have to return the straws. Suppose we are getting the fiber from the flax fibers, that is first in the form of straws. So we are doing the retring process and scrunching and the fiber to scrunching and hackling, and these are the process of producing the fibers. Then the treatment of fibers are there, and fiber conditioning. If the fiber is not uniform and it's in a lot of entanglements are there, we have to make the conditioning of the fiber and in the forming in the unidirectional or yarn and weaving, and we have to do that kind of thing. And then finally we are process fiber processing with the polymer, any kind of polymer like a thermoset or thermoplastic. Then we can get in the flax reinforced composites. So this is the advantages of the natural fiber composites. The renewable and renewable raw material base and also the biodegradable and reduction the reduce the fossil fuels and resource consumption, the lower greenhouse gas emissions and lower overall emission and also the environmental impact. And the advantages I told in the previous slide is the low density and have the high mechanical properties are there because of the cellulose content is very high. And these are some examples currently used in the market. They are using for in the automotive industry. That they need. We don't need many testing and qualification. We don't need. They are used for interior applications because the strength is equivalent to the glass fiber. So we can consider it as the interior panels for automotive industries. And this objective is here we used high density polyethylene as a binder of the resin system here, and we investigate the effect of processing parameter, temperature and pressure on different physical and mechanical properties of compressed molded high density polyethylene biocomposite panels. So here we used high density polyethylene as resin as a binder. And the saline treated, because the saline treatment is we can improve the coupling. That means the saline is a coupling agent. We can get a good addition between the polymer and also the fiber. So it's improve the fiber interface properties. So here the flax fiber loaded is we are loading the 10, 20 and 30% of flax fiber and the controlled samples by weight. And the molding temperature is 150 and 170 degrees Celsius. And molding pressure is we are varying from 6.89 and 10.3 megapascal. And this is a process. Fiber and pre-treatment is using the alkaline treatment or acid hydrolysis. We can try it and size reduction. Then we mix it with high density polyethylene. Then the extrusion process and pelleting and sizing. So finally, the compression molding process will get this already that parameter I explained in previous slide. So we can get the biocomposite boards for various applications. So this is the process where the pre-drying and blending of the compounding of this natural fiber and high density solids. This process is melted here, and because we are optimizing the the screw extruder blades. The twin screw extruder blade, because here we are using natural fiber. If it's a conventional the screw extruder thing, it damage your fiber. So that's why we are optimized that twin screw extruder blades. So here we need to exercise the physical property and mechanical property. Here we study the color analysis and water absorption test for the physical to evaluate the physical properties. The mechanical property, tensile, flexural and hardness test field. So this we consider the to optimize the process parameter. the processing condition of high density the biocomposites, the various temperature and pressure. We are using the temperature is 150 and 170, and also we selected two different pressures for different conditions, C1 and C2, C3 and C4. And this is the sample's ID. Sample ID is the loading, the fiber loading. We are getting 10%, 20%, 30% pure the high density polyethylene samples. So this is the results of thing, because here we mentioned the colored color analysis, the color fading analysis. That here the higher fiber content have a higher the entropy, and melting temperature are high. And here is color index and also the fiber all equal. When the less fiber content have only nearly the 40 to 43% of fiber content is there. So if we increase the fiber content, the value is increasing. So that is we are. I'm trying to say if you increase the fiber content, the color index is going to increase. So this is the density. The same thing here is there, and the density of the polyethylene, if you increase the fiber content, it still is increasing. So we found because the optimizing the fiber content, so we go up to the 30%. If you go on the 50%, its material has become very brittle, and the properties is not the mechanical properties is not good. In other slides, I will explain how the mechanical properties change. The flux fiber density is greater than high density polyethylene. If you increase the fiber content, increase the density. That is we concluded here. And this water absorption is also same. So the high density polyethylene, it is not absorbing the water. The higher fiber loading increase water absorption, because the fiber is its nature is absorbing the water. So that's why. So we concluded here. And this is the tensile test. Here the higher the fiber loading, like 20% increase the tensile strength, because with optimal condition of the fiber loading is 20%. And also here this the colors is indicating the temperatures. We have 4 different temperature and pressures we are using here. The lower temperature is having the good tensile strength. This is a flexural strength. Sorry, it's a Young's modulus of from the tensile test. The Young's modulus is increasing with the higher the fiber loading. And then the strength is in CF20. That means the 20% of Flax composite have a good tensile strength. And here is the higher volume content have a good Young's modulus. The stiffness of the material is high. So the lower temperature is we get a higher tensile strength. And one more result we got it from this test. Then the flexural test. Here the flexural test is also same. The fiber higher fiber loading increases the flexural strength, and same here the lower temperature is better, because if you go in higher temperature, the fiber is get degrade. So that's why we optimized it in the lower temperature. And the optimal the fiber volume is the fiber loading is 20%. And so it's a conclusion. Yeah. So conclusion is the flux fiber serves as a reinforcement, increasing in the fiber loading, increasing the composite color, density, and water absorption. And tensile and bending strength is increased with increasing the fiber loading, but decreasing after 20% of fiber loading. And Young's modulus shows continuous and significant increase with the increasing in the fiber loading. So high density polyethylene biocomposite have a better mechanical property for lower molding temperature. So that is our conclusion. Yeah. Yeah. So this is one part of research in the natural fiber composite we did, and the another thing is I have the little bit about the natural nanofiber composite research in our company. Hello. Yeah. Hello. Is audible?
Yes, sir. Yes, sir.
Yes, sir. Audible.
So currently we are working on this project. This is cellular nanofiber and its application. So the cellular and nanofiber is from it's advanced material. But it's a natural, and also we need an high performance the process we need for to get the bio nano material. So here we synthesize the material from natural, the plant fiber and the wood also. So why we are working on this project? We are developing the advanced and also the sustainable composite material for solving the problems we are currently facing in the environmental pollutions, because there is a lot of waste even in a composite industry and also automobile industry. There is all the wastages are in the landfill. So currently we are trying to find a solution for to reduce the CO2 emission and also the to reduction the weight and the biodegradable material we need for solving this the problems. So currently the composite materials mostly derived from the polymer, the petroleum based materials. So it's not sustainable and also not environment friendly. 5 to 7% of petroleum is used for production of plastics and fibers. So 94% of composite materials and plastics are end up in the landfills. So we are designing the sustainable design. We are extracting from the material from plant and agro, the crops and the agro waste, and also the wood and the wood waste and forestry waste. And that we are processing the material. We are parts developing and assembly and also the product use. This is the end of life is also we are able to recycle. If it's not a recycle, we are put it into the land. It get degrade some years, because compared with the plastics and all, it can degrade within based on their behavior. It can definitely degrade. So we can give that assurance, because we are trying to make a natural fiber and biopolymers we are using. And this is one of our in-house development. We are using the pineapple fiber. We are extracting the pineapple fiber from the pineapple leaves. So then we are do the extraction. Then we are the process treatment, chemical process treatment, and the drying and chopped in the some small fibers. Because due to the time, I can go on fast in this slide. So this is a fiber extraction. We will finally do that alkylation treatment. We can get the pineapple fiber, short fibers. So why the natural fibers? So because in the previous slides, in the previous presentation, I told that we have a lot of natural resources in our country. Even the good example is banana, because banana in the southern India we have a lot of waste also. Day to day we are using banana leaf and banana also. So we have a lot of waste there, and pineapple and scissor. Every these all the resources are available. So that's why we are finding some natural fiber products from this kind of available resource. And this is the properties of the natural fibers. Here the cotton and flax and hemp, core, and also the bamboo and softwood and pine wood. I mentioned it in the properties. The previously there a lot of researchers are working on this, so we can get in data from various researchers. And here is the biodegradable polymers. The biodegradable is also from the natural, the polysaccharides and also the proteins. Some agropolymers and biopolyesters are there, and we can use. We have to select based on our application. We can select the biopolymers. And this is the basic plant structure. So I explained in a previous slide. The plant have various layers, and also the constituents are there. The main component of the natural fiber is cellulose, semicellulose, lignin, and pectin, and wax. And this is a red ring process. We have to remove that the skin of that pipe, because we need a fiber. So the extraction process. So we have to do that is called red ring process. And this is the chemical composition of plant fiber. So the cellulose. This is main ingredients. So from this thing, we have to extract the cellulose and then the nanofibers from here. So that is the process. Is a hemicellulose. We have to remove it in some alkylation treatment, and the fiberization. Next, microfiberization. Next, we have to split in the elementary fiber. That elementary fiber, we have to do it in multiple process. We'll get the nanofiber from it. This is the cellulose microfibrils are there. So here, in the microfibers, there is a lot of the cellulose chains are there. The cellulose chains have a lot of functional groups is connected is almost 30,000 cellulose microfibers into this, and the size of the microfibers are 10 to 30 nanometers. And this is the cellulose nanofibers. The cellulose nanofibers are in the crystalline region and amorphous region are there. And it's a very strong and material. It's already proven in worldwide. They are using for pharma industry and food industry, and also for it's an additive and also the reinforcement agent they are using. So currently we are trying to use it in structural application for strengthening and the insulation applications. And this is a process from the tree or plant. We are doing alkylation and hydrolysis process. Then we have 3 different processes there: mechanical, chemical, and enzymatic process. So here we use the mechanical process. We are drying and crushing, and we are making the pulverization process, nanopulverization process. Then we can get the cellular nanofibers. The further hydrolysis, we can get cellular nanocrystals also is possible to make. And this chemical mechanical method we developed, and after the alkylation treatment, the water we disposed in the water suspension. The grinding and homogenization, we can get a nanofiber suspension like this. And its various applications are there: nano composites and the filter application, and the gas barrier. We can use it for food industries and other the packing applications. And we can use the transparent sheet for many electrical applications. We can use it in the cosmetic and food and coating, and also the other mixes. We can use this and a nanofiber for commercial applications also. But we are focusing on nano composite for automobile and other the rubber additives. We are planning for that. This we have some results. I'll share it with you, because this is cellular nanofiber. Currently, I'm working on it. So the polymer nano composites, currently it's in a trend, and the various industries and also universities are working. And here he mentioned that the cellular nanofibers and also the nanocrystals. The nanocrystals in the form of rice it's individual nanocrystals in individual structure. And also the nanofibers is like as a spaghetti-like structure. It's have a lot of the entanglement that OH group is bonded between the chain of polymers. And this is our development we did. We did the epoxy sheet and CNF film, that the cellular nanofiber films, and we did the compression molding process. We can develop cellular nanofiber reinforced composite films for structural application. This is our small R&D work. And this is a measurement of physical and mechanical properties. And this is a sample development. 50 is the length and gauge length 25 meter. This is the scaled down model, because it's based on the standard we used. And this is the results for the impregnation of resin. If we increase the CNF, only the 20 to 60% of cellular nanofibers having a good mechanical and physical properties, and also the impregnation is very good in it. This is a truss strain curve, and the truss strain curve is mentioned here is a 0.51, and because this is a nanofiber, so only we are loaded in a very low percentage, like 0.5, because the 0.5 surface area is very high, right? So that's why we are loading a very less thing, because all the nanomaterials are surface the surface density and surface specification, and it's very high. So that's why we use very low percentages are there. Here we have the different resin systems: high viscosity, low viscosity, and medium viscosity. And the low viscosity resins have a good mechanical property compared with high viscosity resins, because of high viscosity resins its impregnation is very difficult, because higher viscosity is just deposited on our film, but the lower viscosity is it's impregnated into our nanofilms. This Young's modulus for the different types of nanofibers we mentioned here. The impregnation, as I told, in the lower viscosity resins is very good in it, and so we can get a good stiffness and mechanical property in a low viscosity resins. The same in the Young's modulus, the volume fraction and Young's modulus, we can get in same the lower density resin systems, and the 1% of cellular nanofiber have good mechanical properties of Young's modulus also, and the volume fraction is up to we reach 60% of volume fraction, and Young's modulus is 0.8 to 0.8 GPa, and tensile strength is 77 GPa. This is our final result we achieved, and the best mechanical property for one weight percentage. This is the surface, the fraction surface of our composite flame. We have to find how that the epoxy resin is going to impregnate it. So we did that fraction test, and there is some the fiber, and we can clearly observe that fiber and the resin bondings, and we can get a good impregnation property. We confirm our composite films have a better impregnation using the FESM analysis. Then this is the fiber breakage thing, because we find the FE analysis, FESM analysis. The fiber fraction revealed that pullout of nanofibers or thin fiber bundles with the diameter of sub-micrometers very closely observed in the FESM analysis. Finally, we can get the clarity on it. The nanofibers is also the pullout mechanism. So currently, what the thing is, we are thinking. So we have to find the breakage, the failure mechanism of nanofibers. So that is a new the trend is going on. If we are using nanofibers or nanomaterials in it, so we have to study the failure mechanism of that material. So here we try to observe what kind of mechanism, the failure mechanism has happened, and we found some fiber full out, and also the resin breakage. The resin is also there. Some is we observe, but mainly some fiber pull out we observed it in our research. Okay, yeah. It's a conclusion of this. This CNF. The nanocomposite films were successfully produced with hot press technique with a lower viscosity resin. We achieved around 60. Revealed that the 1% of CNF preforms with a lower viscosity epoxy resins have good mechanical properties. The Young's modulus and tensile strength I mentioned here in 0.8 GPa for Young's modulus, and like 77 MPa is tensile strength. Yeah, that's all. Yeah, thank you for this opportunity.
Well, thank you very much for your presentation, sir.
Yeah.
Really, the session was eye-opening, and I hope the researchers and the teaching fraternity around the globe, those who are attending the program, got an idea. And may I now request the dear participants to post your queries in the chat box, or if you want, you can unmute your mic and you can raise a question to the resource person, Dr. Devendran Thirunavukarasu. Please, one by one. I have a query already, sir, from Vijay Lakshmi Bharati K. So, which part of the banana plant you suggest, stem or leaf, to extract good fibers? This is a question from Vijay Lakshmi Bharati K, sir.
Yeah. Hello.
Yes,
thanks for your question. Actually, you can use stem, and also the banana fruit. They have an the center core. The banana fruit, they have a center core, right? That center core have a lot of waste, because the stage we are using the banana in our for any festival, anything we are using the banana. But that the core is we have a lot of waste. It's not the stem core. I'm saying that fruit, the inter core is there, right? Hello.
Yes, sir.
Yeah. So we have to use stem. The leaves is not that much the fiber content. If it's dried, it's like a sheet. So it's very it's very difficult to extract the fiber from the banana leaves. So we have to use shrimp.
Any
Hello,
other
sir.
queries? Yes, sir.
Hello, sir.
Yes, sir, you're audible,
Hello,
sir.
sir.
Go ahead, sir. Go ahead, sir. Go ahead.
Yeah, I'm Dr. S.M. Ravi Kumar. Sir, for testing, for tensile testing of fiber, what diameter should be considered?
Diameter or length and width of the fiber, sir?
All the things.
Yeah, the length currently we are using for thin films, we are using 50 mm. That means the standard is based on the sizing is there. So in the ASTM standard, the D3039 for tensile, it's 250 by 25 mm. But here we are using the scale down because our films, if usually we have two different types of samples developments. One is if you are making a 20 mm plates for natural fiber plates, that means the composite panels. That time we can take as per the ASTM or ISO standard. So 250 by 25 mm and 2 mm thick. For the thin films, for the thin film, if you are going to make 100 microns or 200 microns films, in that case we have to consider thin film standard.
Sir, for all the fibers, means these biofibers, same test will be there?
Yeah, same. We can follow the ASTM
same specimen, standard specimen?
Yeah, standard specimen. We can follow the ASTM because it's all under fiber reinforcement plastics. So we can follow the ASTM standard for fiber reinforcement plastics.
Thank you very much, sir. Thank you very much.
Sir, this is Kupraj from Hindustan College of Engineering Technology.
Okay.
Sir, I have some of the question.
Yes.
Sir, we are doing many research in the area of natural fiber composite.
Okay.
Sir, if we are doing natural fiber composite process, the one of the tests we called as a ILSS test, right? Interlaminar shear strength.
Yeah.
Sir, what is the? It is provide better ILSS value while compared to glass fiber, the natural fiber composite.
ILS because currently we are doing the basic test is a tensile, right? So the tensile and flexural we have the results, but the interlaminar shear. So we are not yet performed because here currently we are comparing with the natural fiber. We are the glass fiber. We are replacing the natural fiber. The glass fiber into the natural fiber. So that in that case we have only result for tensile and flexural, but interlaminar shear if we can use. But the problem is the fiber and density and also what kind of resin we are using in it. But values, if you want to improve the interlaminar shear of natural fiber, you have to add some filler materials.
Okay, sir. Sir, and I have one more question also.
Okay.
Sir, if we are using glass fiber kind of thermoplastic composite means we can easily make the ply arrangement very easily, sir. Whatever ply arrangement, 0 degree, 45 degree. Sir, how we are doing such kind of ply arrangement in this natural fiber composites, sir? Natural fiber composites.
Yeah, now in the market the unidirectional fabric and woven fabrics are available. So same thing. If you're we are developing the fibers of the natural fiber from extraction of any plants or trees. So that time you have to make it in some unidirectional only. So initially we have to do the Z pinning because we have to make all the fibers are in the single alignment in the direction, like 0 direction. So after that we give some reinforcement for that, or you're buying from the market, they'll give that the preform unidirectional or bidirectional. You can cut it in the direction as per the road.
Okay. Sir, and I have one more question. Sir, we are doing glass fiber means it is having we have 2 meter, 3 meter length panel means we can easily make, because we have a lengthy fiber sheets we have, sir. But if you're having such a natural fiber kind of means, there is, if you provide any joints means, obviously we will get a failure, right?
Yeah.
The failure joint itself, we will get a failure. So how you overcome this, sir? Because if you are doing some lengthy kind of panels, in our slide, if we are using natural fibers in the race car panels and all.
Okay.
So we are using some lengthy kind of panel means. So how you are overcome this? Because this is a shorter elements. If there's a fiber is not a length elements, like glass fiber kind of things. So how you overcome this?
You're saying the fiber mat or
Fiber mat.
yeah, the fiber mat is, suppose we are getting from the market, they already aligned and we can get it as a fabric form.
Okay.
Is it in the fabric form, we can make it any kind of panels or dimensions, that is not an issue. If we are making in-house fabric, because in-house fabric means we have to make the yarns, like fiber yarns, then we have to align in that is the task is very big, because we have to do the lettering process, because in my slide I mentioned the pineapple fiber, right?
Yeah.
In the pineapple fiber, so initially it is in the unidirectional form. So, but after the process, it's very thin, and also it's very difficult to handle. It's broke after the alkylation treatment. So in that case, we have to do the spinning process. That means we have to make that fiber into the yarn. Then we have to do the weaving process. So I think for the R&D is it's very difficult. So that in that case, we are doing, we make it a short fibers or long fibers. That means we have to cut it into the 2 mm or 3 mm or maximum 5 mm, and for the characterization of the material and the fiber properties. So if you are taking the material directly from the plants or tree, you are trying to make the fiber or into the fabric. So into the fabric is a very difficult task. So if you want to study the properties of the fiber, we have to reduce the sizes. So after the reducing the size, you have to mix it in the resin systems as a filler. Then we can study the properties and the fiber the fraction mechanism and all. Or if some fabrics are currently available in the market. Even the pineapple mat is also available in the form of fabric, and the flax fiber is also available. Some companies, they are selling in the fabric form. So if you are taking specific material, if the is not available in the market, if you want to make that material, so the fiber, you are planning to use that fiber into your research, in that time you have to think, if your panel is 30 by 30, you will try to form it in the unidirectional. In that case, you will study the property. If you want to make the more than 300 by 300, it's very difficult to make. So again, we have to reduce the size of that material. Suppose it's a 300, you have to cut into or chopped into the 1 mm or 2 mm, like that.
Okay, sir. Okay, sir. Thank you, sir.
Thank you.
Yes, sir. We have 2 more questions. Sir, are you here?
Yes, yeah.
A question from Mr. Sultan. Yes, sir. Which type of resin will give perfect result for natural fiber composite?
It's better for R&D. You can use epoxy system. So epoxy is a better solution, because other polyesters and all is not better. For R&D and also the product development, is epoxy is a better. Or if you want to use biopolymers in your research, you can use PLA, polylactic acid, or some bio epoxies are available in the market. You can use that also.
Yes, sir. Thank you. And a question from Mr. Meghavannan M. Regarding the fiber reinforced composite, I have one concern. Please describe the quasi-static sequence used in fiber lamination approach.
Yeah, the quasi set. Yeah, that's why in the previous question also I answered, because if the lamination is not an difficult, because currently all the fabrics are available in the market, so you can get that in the fabric form. Is very easy to cut it in different directions, because we'll get the unidirectional fabrics and also the woven fabrics. In some, if the specific material, like if you want to make some other, for example, if you want to make kind of the banyan tree or any other different trees fiber, in that case is not available in the market. In that time you have to make that the fabric in the UD form, then you have to cut it. That is that task is very high, very big task. You have to make spinning and weaving, and it's better if you want to study the natural fiber properties, if you go into the short fibers, because if the material is not available in the market, you have to cut it into the smaller size. It's chopping is very easy, because we have to cut into the minimum 3 mm and maximum go up to the 5 or 10 mm. You can cut it and you can study the properties of material. The characterization is everything is we can do. If the commercially available the fabrics, natural fabrics, you can cut it into the quasi-static minus plus or minus 45, 0 and 90 is able to cut.
Sir, I have one question, sir.
Yeah.
May I? Hello?
Hello.
Yes, sir, you may proceed.
Yeah, myself, Dr. Krishna Gowda. First of all, I would like to thank the organizer and Dr. Devendra sir for the nice presentation. I have one question actually. As per the presentation that what I observed, if you are using this fiber-based polymer composite, then we are able to get better strength. But whenever you are going for the the natural, the nano-based fibers, then at that time the strengths are very less. Am I right, sir?
Strength is not less, sir, because the fiber, the surface is very high. So the surface
Yes,
area
yes.
is very high. So in that
Sir,
case, hello.
yes, sir.
Yeah. So suppose if you are giving us 1% of nano filler, like a nano fiber in the sense, so
Yes.
it's the main thing is how we are going to mix it. Like we need the mixing. We have to mix it in a homogeneous. Or if it's in a lot of agglomerations or the entanglement is there, it's affect the property. So the processing is a very important factor.
But what for the experimental observation, what I also obtained, whenever we are going for these nano fillers, we are not able to incorporate much amount of filler in comparison to the
Yes,
fiber based.
yeah. That why, because with that optimal condition is there. If you go into the more proper thing, and it's affect the properties, because we have to optimize the how much volume we have to give that nanofillers. Because even in a cost is also very high. If you are using a more material, suppose for example, if you are using a carbon nano materials like a carbon nanotubes, so in that case, if you are using a more percentage cost and also property, it will there. So it's better before going to the thing, and we have to optimize the loading of nano fillers. Like from start from 0.1% is also we haven't some changes there in our. If you put the 0.1
Yeah.
percentage of nano filler, we haven't get some
Yes.
improvement in functional and also structural improvements in that.
Yes. These are the few actually experimental observations I also made.
What
That
kind of
whenever you are this,
material you used in your research?
I used graphene actually.
Yeah, the graphene. Yeah, we also use the graphene, but we are using graphene for structural and also as well as the functional application.
Yes.
For the
Yes.
structural part, we used for to improve the flexural strength of one of our component. It will increase the flexural strength actually. If you use only 1%.
Okay. If you can permit, actually, I can make a contact with you so that more discussion I can do apart from this
Okay.
conference time today. Okay, that will be.
Yeah.
I will be thankful in that case much more.
Yeah. Sure.
Okay, sir. Thank you, sir. Thank you.
Thank you.
Yes, any more queries, sir? The
Uh,
participants. Yeah.
Good morning, sir. This is Sultan from Sanjay Godawat University. I have one query. Sir, is this possible to use the wastable, non-reusable plastic as a short fibers in the composite materials?
Yeah, that is also possible. One of our research is there in the same what you told. We are working on it.
Okay.
But the thing is the processing, because each plastics have a different temperature and the pressure we need. If you are
Yes,
in a
sir.
polypropylene or ABS or a nylon, there's a different temperature. If you give a higher temperature, because if you want to use nylon, the nylon temperature is different and polypropylene temperature is different.
Yes, sir.
So we are planning for one process development for if you are using all the combined material, because here the shorting of that material is the bigger task.
Yeah.
If you have the plastic waste from all over India or for one small region, we have to collect that material and we have to segregate into the different category. That is a bigger task.
Yes,
So
yes.
in that we have to cut off that cost. We are making all the plastics in a single shuttering machine. Then we have a process. If you give it
Okay.
optimal temperatures, so that is we are working on it. It's possible we can use it, but for the structural part application is very difficult to use for structural applications.
Okay.
But one more option is there for we can mix it. We can melt that all the plastics and we can convert it into the other resources like
Okay.
fuel, and currently the biofuels and some the plastic also they are trying to use it as a fuel right now.
Okay,
So
sir.
we can use we can melt it and we can convert it into the fuel. That is one thing is there, because
Oh,
all given a higher temperature, if
okay.
lower temperature materials get degrade and we can get in some the resource for fuel.
Okay, sir. Sir, is there one more question? If I use it as a short fiber, as that plastic means that LY556 give a good result, sir.
Okay, so you're saying that you have to shudder that fiber into a short fiber.
Short plastics.
Short plastic. So
Uh,
what you're shuddering or chopping? What kind of technique we are using for that?
Chopping, sir. Chopping is a small pieces and then make it a unidirectional short fibers.
Okay.
For that, that
Unidirectional short
LY556 give
fiber.
yes, sir.
Unidirectional short fiber, or it's a short fiber itself. It's randomly oriented.
A randomly oriented short fibers, sir.
Okay. Okay. So you can use LY556 because you are trying. It's not a compression or process. You're just going to mix that plastic as a reinforcement. There is no further production of there. So you can
Okay.
use LY556. You are trying to use as a filler material, right?
Yes, sir.
Okay.
Okay, thank you, sir.
Thank you.
Thank you.
Any more questions? Kindly post the questions. Is there any more questions from participant side? Dear fellow participants. How to select the processing temperature? Question from Manikandan R. Sir, how to select the processing temperature?
The process temperature is based on the polymer we have to select. If you are using thermoset, there is room temperature process also there. If a higher temperature epoxy is also there. So based on the binder, here the fiber is not an issue, because fiber is just give the reinforcement, and all the fibers are it's withstand more than 500 degrees Celsius. So here we have to concentrate on selection of polymer. If you are select the PP, the polypropylene, so in that case we can select go up to the 100 degree. So if more than 100 degree, it get degrade that transition temperature there. So before selecting the material, you have to find the properties and also the glass transition temperature and melting temperature, the melting point. So based on that, you have to select.
question from Dr. Satish. Sir, do you support composite filament development for 3D printing applications? Do you support composite filament development for 3D?
Yeah, currently we are also into the this kind of project, but this collaborated with the VIT Chennai, but still we are facing some issues because the fiber reinforced thing is we have to develop, we have to work on the nozzle and also the feeding thing. It takes some time. Currently, we don't have any facility for that, and we are developing that the project.
The question from Mr. Ganesh Kumar Judge. Whether this will Biofiber composites use.
That's why in the presentation, the Flax composites, I'm said that we are planning to use interior application, but the certification agencies like DGCA or FAA, they have to certify the material for, but the exterior application like a fuselage and wing is very difficult to use. But that all the structural member and high impact and low impact are there, but some interior parts and also the inside the aircraft, there is a lot of non-functional structures are there, so we can use. But before the use the natural fiber into the aerospace and the aviation, the aircraft manufacturing application, so we have to get the approval, approved materials. So I hope maybe the European Space Agency, they will give some the norms for using the natural fiber composite, because currently the Airbus also, they're working on the same kind of the natural fiber project for interior application. So we hope in short time we will get an what kind, because they have to suggest if they the flax fiber or the natural, they have to give that the certification for the material and the supplier. So then only we are practically we are using that material. But R&D purpose, we can study all the things, acoustic and also the noise absorption test of and also thermal insulation. These are the testing. So we have to, because worldwide there is a lot of researchers are working on the same kind of research.
Is there any more questions? Any more questions from participants' side? So I hope we can close the question session.
Sure. Okay.
Yes, sir. So thank you very much, sir.
Thank you.
We are very much obliged and thankful for your wonderful presentation, for accepting our invitation and brainstorming session. So thank you very much for your valuable presentation, sir. We'll send the feedback and the overall response from the participants to your mail ID. And can we share your mail ID and details to the?
Yeah, definitely. You can share
your contact details, right, sir?
Yeah, sure.
Okay, thank you very much, sir. Thank you for being here, sir.
Yeah, sure. Thank you all for this session.
Yeah, dear participants, thank you for joining the session. Hope you had a wonderful session and you have learned a lot and you have gained a lot of knowledge and details, information from the resource person. And the afternoon session will be starting by around 2:30 p.m. sharply, and our afternoon session's guest is Dr. Indrani Sen, the associate professor from materials and metallurgical engineering, IIT Kharagpur, and the topic is nickel titanium based shape memory alloys. So we'll be meeting you again around 2:30 p.m. and join the session on time, and the meeting links will be shared in both the WhatsApp groups. Thank you very much.